the use of what's called cache memory. So cache memory, from the French word cacher to mean hidden. And quite why it's supposed to be hidden, I'm not quite sure. When you find cache in a computer system, it's supposed to be hidden, but I think it's something that the user's not actually aware of. In that sense, it's hidden. So I'm going to introduce you to the idea of assembly code, and that's just another way of talking about a language which the computer system can actually understand. And to talk a little bit about the idea that a computer's instructions are stored in computer memory as sequences of binary numbers. So it'll all be made clear, hopefully. Don't have to worry about any of this. And I'm going to show you how to write a very simple but quite interesting program in assembly code, and I'll do my best to explain that. And it's very much up to you to stop me if there's something you don't understand. So, time permitting, we'll have a look at some Python programming language. And there are two things that I think are very important. Firstly is, how do you define a function in Python? And how do you actually use while loops? I mean, Mohammed, as far as I know, I mean, you might have done 2 years work on Python and computer science, or you may be coming into computer science for the very first time. I don't know, but you can tell me if you think it makes a difference. So, as a bit of information, there are 2 documents, and I'll tell you where to find them right at the end. There are 2 documents that you could have a look at, and they're extracts from the book I recommended right at the beginning of the computer science course. I mean, I think it's by Duddle and Duddle, and it's something like A-levels computer science. So I've just given you 2 short extracts called, I think it's Introduction or Basic Hardware 1, Basic Hardware 2. It's just 2 very short documents, but they're quite readable and you might find them quite useful. The other thing is that I've given you somewhere, I'm not quite sure where, somewhere in the topics I've given everyone a free electronic textbook, and it's got a really odd name, but I'll try and remember what the name of the book is in a moment. So and you might find that as a sort of quite interesting general background book, a book giving you some of the basics, and it's written quite clearly but quite informally, so you might find that worthwhile. Okay, so without wasting any more time, if there's anything you want to ask me now, then go ahead and ask. Although we've got a slight disadvantage in having to type to one another, but we'll see. Okay, so I'm going to... Thank you, Mohammed. Okay, so I'm going to load the first 2 main presentations up on board, and okay, so the title of the book I've given you is a really strange title. It's But How Do It Know? Well, it's really odd, and I can show you an extract a bit later on if you need me to. So, okay, so I'm going to start off with, if I can find it. Okay, here we are. Got no again. I think hopefully it's this, or else I'm just going to have to go back to the drawing board a little bit. No, that's not it either. I do apologise. Try again. Hopefully, okay, I think I've got it now. Third time lucky. Let me get rid of these. Hopefully it's going to appear. Okay. So can you see this quite clearly? Is that okay? Okay. I mean, I think you can make this area larger if you want to. So I'm looking at computer architecture, and specifically I'm looking at a very simple computer design, and I want to explain its operation in some detail. So the architecture of a simple computer is presented here, and its operation discussed. So I'm repeating myself, okay? It is, okay, so it's actually very important, I missed out the word important here, that at the end of the session, it's very important that you will understand what I call the fetch, decode, execute instruction cycle. And it's important because the cycle of operation, given this name, really explains everything to know about the operation of the computer. So it's a repeated cycle. You're repeating the fetch operation, then you're decoding an instruction, and then you're executing it repeatedly. And a computer is capable of going through that cycle in a few milliseconds, if not, in some computers, a few nanoseconds. So what a fetch, decode, execute instruction actually represents is a tiny bit of work done by means of fetching an instruction and executing it. So, and the reason I'm showing you all this is that you might want to attempt the coursework that I've set others. And as I said, if you want a bit more time, then that's fine. There's something like just 4 questions, and I can show you, when I've finished talking about computer architecture, I'll show you the assessment paper. So anyway, to continue, for most people, a digital computer is a black box into which we enter data, or it receives some kind of input. And what comes out of the black box is some result that we want, some result that we expect, or help on how to do something. Most people simply don't care how this happens, as long as it does that and it produces results quickly and correctly. And one concern that we might have is, well, how quickly can the computer be programmed or reprogrammed to perform a specific task? Now, it might be simply to do a mathematical calculation, that it's more effective to let a computer do it rather than for us to spend weeks doing it by hand. So, and the question in that case is, how long is it going to take you to write a program to do that? Well, we'll try and answer it a bit later on. So, in the very early days of computing, and I'm talking about some 50s, 50, 60, something, about 80 years ago, when people like Turing were using very basic computers to break the German World War II code to enable, to give British armed forces some kind of advantage in knowing what the German forces were proposing to do and how they were going to do that. So I'm just going to make this a little bit bigger at the moment. So a program might have looked like this, and it would simply consist of a very large number of sequences of ones and zeros and nothing else. And maybe in a short program you'd have 30,000 symbols. Right? And part of the job of the computer is to understand what all these ones and zeros mean. I mean, what the computer is going to do is to interpret, say, a string of ones and zeros to mean a particular instruction or a particular data item, and then set about to operate on that data, and at the end of the program some result will be presumably stored in the computer's memory or visually displayed or something along those lines. So obviously, who in their right mind actually wants to write a program which has to consist of ones and zeros? I mean, supposing there is a fault in the computer, where would you begin to look for the fault? And who could just look at this computer program and tell you straight off what it's intending to do? And who has got the infinite gift of being able to tell you whether what you've written here is actually an error-free program? Well, these are obviously quite good questions. Anyway, let's start at the beginning. What do we mean by a computer program? It's simply, all I mean by a program is a sequence of instructions which involve both data and operations on data. So it could be at a very top level view of what a program is. It might be simply to add two numbers together and produce their correct sum. Right, so look again at the program I've just shown you. It shows a long sequence of binary numbers, and who can say simply from looking at these what the program does or whether there are any errors in it? Very, very, very difficult. So obviously things had to change, and some other way of representing computer instructions was necessary for people like you and me to actually come to understand what the program was actually going to do, what it means. So what we're going to do now is to take a careful look to see what the architecture of I keep stressing this, a very simple computer looks like, and how a program such as the one above executes to produce a result. So what I want to do first of all is to tell you about the main components of a computer. And in the literature, if you do any reading, it's generally accepted that there are three main components that constitute a computing device. And the first is the CPU, which simply stands for the Central Processor Unit. And you may already know that many laptops actually have can have several processor units. I mean, they're called multi-processing laptops. as opposed to a multi-threading laptop, but we'll discuss all this a bit later on. And the second main component is main memory, into which data and instructions can be stored, and out of which those instructions and data can be output, or in the terminology of memories, can be read. And thirdly, the input and output controller. What the input-output controller does is to issue a sequence of hardware signals that results in a particular operation to be achieved. For example, an input-output controller might be responsible for some results being displayed on the computer screen, or the input-output controller might be responsible for controlling the keypad or the input device that the particular computing device uses to get input. I mean, it might ask you to input data, and in the current days of quite advanced laptops, I mean, maybe the controller is actually going to be responsible for displaying the most amazing graphics displays on your screen, or maybe it's to send data out on your Wi-Fi unit onto the internet and to receive data from the internet. So these three components are interconnected by means of special groups of parallel wires. Typically they're going to be parallel wires. So just imagine three wires literally, physically running in parallel, existing in parallel, and they're connecting unit A to unit B. So A can communicate with unit B by means of a set of parallel wires. In other words, you can transmit data one bit per wire at a time, so you can actually transmit data in parallel, which is much faster than sending the same amount of data serially. First of all, you send the first bit, then and only then you send the second bit, then and only then you send the third bit, and so on. So the name given to this wiring of connections between the CPU and the memory and the output controller are called buses. And I think historically the term buses actually originates from an omnibus, which is simply, in London anyway, were used to transport people. So in the case of computing, I mean, buses are used to transport data in parallel, just as omnibuses, and I think they were horse-drawn to begin with, would transport, say, 30 or 40 people simultaneously from A to B on the streets of London. So next thing is that there are three sorts of buses. And the first is what's called a data bus. So again, it's like, let's agree to say that it's eight parallel wires in order to transmit data, 8 bits of data at a time. So you're using a data bus to transmit data. And the second kind of bus is to transport or transmit an address. So they're called address buses. And we're going to find out that in order to use the services of a particular device within a computer, it's typical that you need to address that device. I mean, maybe it's to address them to read data from memory, for example, or maybe maybe you want to address what's called a register, which is connected to an address bus that enables you to select that register in order to put data into that register or to read data from it. And finally, so I'm just giving you a sort of very general overview of what buses are and their function and their role. There are control buses, and a control bus consists of one or more control signals, so an electronic control signal, and these signals will come from a controller at the particular time that you need to perform an operation. So, for example, we were just talking about memory a moment ago, but maybe you want to put some data into a memory, in which case you need to do two things. First of all, you need to put a memory address onto the address bus and put that into a register close to the memory, and then you issue a hardware signal telling the memory to perform a write, what's called a memory write. So you're taking some data that you put on the data bus, and you need to know where to put it in memory, so you use a particular address. And then thirdly, logically, you can issue the hardware signal to main memory saying, look, I want to write the data that I've just put onto the data bus into main memory at a particular address or location, and that'll all happen. So data buses allow data and signals to flow from one of these three components to one or more others. So you can transfer data from the CPU to memory, or from memory to the CPU, or maybe from the CPU to the controller. I mean, maybe you want to send some data out onto the internet, so you will probably want to send the data you want transmitting to the controller, and then you tell the controller that you want that data to be transmitted over Wi-Fi or something along those lines. So control buses enable the three components to be controlled, in other words, to perform their functions as or when needed. I mean, you can think of a control signal as simply some kind of, I mean, it could be something like to use the analogy of somebody blowing a whistle to make somebody jump to attention and to perform a particular action, or maybe two blows on the whistle to get somebody else to jump to their agreed action and to perform it, and so on and so on. So control buses enable the three components to be controlled. So, for example, I might want to tell the CPU to perform an addition operation. That's fine. Okay, all I have to do is to send a hardware signal to the ALU, what's called the ALU, to perform that operation, and it's done by hardware. Okay, so all this will become hopefully very clear later on. Okay, so from the top left, from a bird's eye view of a computer, we've got the three components here. We've got the input-output controller, we've got the main memory, so it's just a block of memory, which we can perform exactly one of two things, two operations on. You can either read data or instructions from memory, or write instructions or data to memory. So it's just two inverse operations, as it were. you've got the CPU, and that, again, we can have a look to see what's inside of that in a moment. But notice the connection between all three devices by means of the three data buses. So I've got just three lines here, and each line represents say an 8-bit bus. So CPU's connected by means of a data bus to the memory. So maybe a controller will say, okay, bring me data from a particular area of memory, maybe it's this little chunk of data here, bring it to the CPU. So memory will be read, the data's put on the data bus, and there'll be control signals making sure that the data arrives at the CPU. And two additional things I'm showing here is the keyboard for enabling someone to put data into the system. The input-output controller can accept data that's typed in at the keyboard and maybe transfer it to wherever it's needed. As well, we've got a screen or a VDU, some description that will actually, when the IOC tells it to, represent the data up onto this screen. So three buses are shown here, and a bus is a set of parallel wires, so three buses. I mean, it looks as though I've got a 3-line bus here, but it's actually three separate 8-bit buses. So this is what I tried to explain a bit earlier. I mean, I'm showing an 8-bit bus. I've got 8 parallel lines, and this simply means that device 1, if it so chose to do that, could send 8 bits of information on these 8 wires to device B, device 2, and it can be done very, very, very quickly indeed. And you're sending data in parallel, not in sequence. And there's no reason why device 2 shouldn't talk to device 1 and going the other way, if needs be. So let's think a little bit about the CPU. As I said, it stands for the Central Processing Unit. You can analyse that in terms of 2 main components. So the first is the control unit. So don't confuse this with the input-output controller. Talking about another control unit, CNTL, which I abbreviate by CNT, short for control. Right. And secondly, you've got something like, I mentioned this earlier, the ALU, Arithmetic Logic Unit. And this is a little chunk of hardware which is capable of performing the very basic logical and arithmetic functions like addition, subtraction, and some of the logical operations. I mean, logical operation might mean simply that you want to move the number stored in the ALU 1 bit to the left. But we'll worry about that a bit later on, okay? We might have the opportunity for considering the logic operations. Or maybe you want to AND or perform the logic OR operation on 2 8-bit words, okay? So each of these components is connected to a register. So let me tell you what a register is. It's just a small chunk of memory, and typically the size of a register is 8 bits or 16 bits or 32 or 64 bits. It's capable of storing 8 bits of information. And each of these components is connected to its own register. So the controller is connected to a register called the PC, or the program control register. And that has a pretty important role to play in the overall operation of the computer. And the ALU, the Arithmetic Logic Unit, is connected to a register that's very often called the accumulator. So we've just got two registers here. So this register is connected to the controller, and this register, the accumulator, is directly connected to the ALU. So let's have a look at the top view of that. Well, no, I haven't got a picture yet of that. So for the time being, so a little explanation of a register, which I've already just stated. So the two registers I've mentioned are connected to two of the three kinds of buses. We'll control the reason for this later on. So three sorts of bus, as I've stated above, don't forget that. And this is what the CPU looks like inside. No, this should be looking at this. That's the CPU exploded. Right, so we've got a controller here, and that's connected to the PC register, and the controller is going to be connected certainly by a data bus and a control bus to the ALU. And the ALU is connected to the AC register, the accumulator register. So maybe the accumulator can put a result into the accumulator of adding, say, 2 and 2. Put it into the accumulator here. Or the accumulator can actually read what's in this register and maybe perform an operation on it. So the PC, should I say a word about the PC? The program counter. What the program counter contains is the address of the next instruction to be executed. So in the steady state, the PC always contains the address in memory of the next instruction to be executed. Right? And we'll have a look at the operation, what happens, how all these hardware units actually cooperate together to make a working computer. And here, notice the directions of the arrows in the CPU. So you've got bidirectional communications in both directions with this register. So this, I guess, this is going to be a data bus. That's going to be data bus, and again, these two are going to be data buses. So think about that a bit later on. So after the program counter is loaded, in other words, after when the system starts up, the contents of this register is going to be loaded with a particular memory address, and its contents are going to be used by the controller to control the operation of much of the rest of the computer's hardware. So it might instruct the computer to move data into the ALU and then perform an ALU operation such as multiplication on the data, or numbers placed or routed into the ALU. I'm going to explain that in depth anyway. Okay, but before I do, let's have a look at the memory component. So we're looking at the block of memory, and so if you can see that it consists of two components. The first is called a decoder, and the second block, hardware block, consists of a series of word storage. So each one of these lines is capable of storing, say, an 8-bit word. So the second parallel line is capable of storing a second 8-bit word, and so on. I mean, maybe you've got 4,000 of these, I'm not sure, it depends on the system, okay. And this quite important device, order decoder, and so cutting a long story short, what the decoder does is to receive probably from, I think I've got this right, from the program counter, the address, which is going to be put onto the address bus, and then the controller within the CPU is going to say, okay, well, I've just put an address on the address bus. I want you to read the word that's being addressed onto the data bus and send it back to me. Right? So what the decoder does is to take an address formed from 8 bits, 8 binary bits, and it's going to perform like a function. It's going to return a unique integer which represents which of these, I don't know, 2,000 words is being selected. So it could be the first, and the first you put in a 0, 0, 0, 0 8 times or whatever. What's actually going to happen is that the decoder is going to output a 1 here, which is going to be used to select this word, and having been selected, all that the CPU has to do, or the controller within the CPU, using the control bus, is to say, look, I want you to read memory at that particular address. So let's have a look at the idea of a memory address. So the decoder, supposing you have 8 items in memory, I mean, this is, just sort of simplifying things enormously. Supposing you have a memory just containing 8 words, and you wanted to name each by a unique pattern of bits. Well, it's very easy. All you need are 3 bits. And why? Why is that true? Well, 0, 0, 0 in binary is number 0. So you could use that number to uniquely identify the first word in memory. So the decoder is going to take 0, 0, 0 and output, 0. It just means, okay, this is the word I want to do some action on. Similarly, 0, 0, 1, which is 1 as a binary number, is just going to give you a 1. So you've got 8 unique labels or numbers which are sufficient to be used by the decoder to return a signal that selects a particular word. So if you input a 4 into the decoder, what you're going to get is a selection of the 4th word held in memory. So hopefully that's not too unclear, and that's reason. So these 8 binary numbers will do the job of labeling or addressing all the words in memory uniquely. I mean, that's why they're called addressers, really. So you've got 8 possible addressers that uniquely address or label or refer to the 8 words held in memory. So we can use the electronic addressers, for example, 000, 001, as labels to refer to any one of the words in memory in a unique way. Okay. So the role of a decoder is simply, from an abstract point of view, it takes an address, and the decoder is actually going to output a signal which activates or enables a word of memory, and it can do that for each word stored in memory. And if you'd like to think of a decoder as having the function of a many-to-one function, do. Think of it that way if you want. Okay. In a little bit more detail, so we're rapidly descending to looking at hardware here. So assume the address bus has 3 wires. Here are the 3 wires. So what the role of the decoder is, if I input a 0, 0, 0 here, this wire is going to have a 1 on it. It's going to have a 1 on it. This will have a 0 on, 0, 0, 0, 0, 0. So 0, 0, 0 is going to have a unique output, and it's going to be a logic 1, a 1 here. And that enables me to either read or write, depending on the incoming signals from the CPU's controller. If I've got data stored here, then a tiny little bit of circuitry here means that I can actually read the contents of this storage cell, single bit storage cell. And if it's a 1, I'll get a 1 coming out here. If it's storing a 0, I'll get a 0 coming out here. And so too with all the other bits of storage in this particular word held in memory. I mean, I can read or write, depending on which signal I give it, data into or out of any one of these 8 storage cells. And all I'm saying is, I haven't given you the detail of what one of these little squares look like, but all I'm saying is that this little square here is capable of storing a 1 or a 0. And I can, with a tiny bit of circuitry, read the data stored in one of these little cells, 1-bit storage cells, or write data to them. So hopefully that's given you a bit of an idea of what's a little note on there, just to repeat what I've been saying. And what does each memory cell look like? Well, little note here, each wire coming from the decoder runs from left to right. Wires coming in at the top are read-write lines coming from the CPU's controller. They run from top to bottom. Yeah, well, I've really shown you all that. Okay. So if a word is selected by means of a 1 coming from the decoder, so that words are enabled in order to write data, so for example the write line is 1, the data will be captured in that cell. If it's selected by a 1 from the decoder and each cell is enabled to have data read from it, the data that was stored in the cell will appear on the data bus. See the bottom of the diagram on page 18. Well, I'm not sure about, I've got that, but it sort of gives you roughly the kind of thing. And I hate to terrorize you by showing you this, but it's actually very, 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 very simple. Right? And so let me give you a very, very brief explanation of this remarkable cell description, this architecture of a single storage cell. And it's really, when this was invented quite a long time ago, it completely revolutionized computing. It made computing possible because it made it possible for memories to store programs, and it made it possible for memories to store results, or simply to remember data for long periods of time. I'm going to just describe it its operation very, very, very quickly. What I've got here is called an RS flip-flop, and this is R for reset and S for set. Now, if I put in a 1 signal, or logic 1 signal, into R, that has the effect of changing from whatever the value on the Q output was to a 0. And the inverse operation of this is that I can put a logic 1 onto this, I guess it's a terminal, the S terminal, and it has the effect of, no matter what was on the Q output before, it's now going to have a 1 output. So it's reset gives you a 0, and a set gives you a 1. Now, supposing, just for the sake of argument, the cell has already been has already been set, so I've got Q equals 1 here. Q equals 1 here. Now, supposing I'm selecting this particular cell, I mean, how would I do that? Well, I've got a line coming from the decoder, and it's going to select every cell in this row, and it's selecting it by putting a logic 1 here. So I've got a 1 here, and I've got a 1 here. And supposing I want to read whatever the value is here, well, we know it's a 1, so let's try reading that out. So we put a logic 1 here, and we've got a 1 coming in here. So we've got a 1, a 1, and a 1. And this is a 3 input. So I'm sorry if I've never ever seen a symbol like this before. It's the symbol of an AND gate. And if all inputs of an AND gate are 1, that's going to output a 1, which is true. You've got a true here, and a true here, 1 here, 1 here, and 1 here. You're going to output a 1 here. So your output is going to be 1, which is correct. You just read value that's being stored in this little box here. On the other hand, if you want to write data into this cell, what you're going to do is to put, I think, 0 here, and this little unit is going to invert. It's called the negation gate, or the not gate. It's going to invert it from 0 to 1. That's going to be a 1 here. And if you wanted to store a 1, let's suppose this is your input, you want to store a 1 in this blue device, you put a 1 here, and okay, you've got a 1 here, and this is going to be inverted, so you get a 0 here. So definitely, because this is an AND gate, you're going to get a 0 here. Alright. Okay, so it's going to have no effect on the R terminal here. R only comes into operation if you put a 1 here. So you're selecting this, let's supposing this is 1. Okay, so you've got a 1 coming in here, and you've got a 1 input here, and you've decided to write by putting a right equals 0 here, so that's a 1 here. And what happens here, if you look carefully, you've got a 1 and a 1 and a 1. Therefore, you've got a 1 coming out of the AND gate. That's actually going to trigger a set input. In other words, Q becomes 1 forever. Right? So you're now in a situation where you've actually been able to store a 1 in this very simple single bit storage cell. And so what I'm showing you here is, okay, it might be a bit unfamiliar, but I think you can follow my way of reasoning about it. It can do one of two things. You can store data in it, or you can read data from it. And all I'm claiming for it is its operation is very simple, but the consequences of being able to build memory using this device is quite astonishing. It revolutionised the whole of computing for lots of different reasons. And okay, well, you've got a circuitry for one bit of storage here, but I could actually make a billion of these and just string them together. I could have a row of a billion of these devices, and that's given me an immense storage capacity. A lot with a billion bits of storage to represent almost anything I want to represent. So I've given you a little description, short description of what I've just been talking about. Okay, so just for your reference. So part two of this little discussion. So let me just check back with you. So are you okay, Mohammed? I'm sorry. I mean, you might feel a bit okay. I'm pleased. But, I mean, give me some feedback by email afterwards if you like. Tell me how it's all been going and what you think about things. Right. So let's just carry on for a while. If you want me to halt for a break, or you want to go and get a glass of water, let me know. All right, and I'll pause. Everything is being recorded, though. All right. So how does our computer, as I've described it so far, how does it operate? Well, first of all, and starting arbitrarily here, we need to understand a little bit more about the ALU. So the ALU performs arithmetic and logic operations. And amongst the arithmetic operations it can perform are negation, addition, possibly multiplication, and division, subtraction, and so on, and so on. So some very, very simple operations. Now, if a number is present in the accumulator register, and the computer is instructed to add this to a number stored in main memory, the result of doing the addition will be put into the accumulator. Alright, so just remember that. So typically what might happen is that there's a number already in the accumulator register. And remember, the accumulator register is a register that's closely connected to the ALU. And if the computer is instructed to add this to a number stored somewhere in memory at a particular address, the result will be put into the accumulator. But what I've missed out there is the assumption that if the computer's to perform that operation, it's got to fetch the number from main memory. First of all, bring it all the way back on the data bus to the CPU, to the ALU. And then the ALU's got to be instructed to add the number that's just arrived to the number already in the accumulator. And finally, the ALU's got to be instructed to put the result of adding the two numbers back into the accumulator. So you're losing the contents of the accumulator. You've just added a number to it. Now you're replacing the original number by the result of adding the two numbers together. So okay, that's a little bit it's made a little bit of progress, because I've half described what's involved in performing an addition operation. But the obvious question that arises is this: how is data put into an ALU? And how is the ALU instructed to perform a given operation on, for example, two numbers? Well, the first part's easy, and each of the two numbers will originally be stored in main memory. So I've just spoken about, suppose that there's a number in the accumulator, and it's required that another number stored in main memory needs to be added to the value of what's in the accumulator and the results being put into the accumulator. So what's needed first of all is to read memory so that each number is actually put onto the data bus in turn. The first number will be routed into or placed into the accumulator, and secondly, the result of performing an operation on the number in the accumulator, and the second number, this sounds a bit tedious and repetitive, but will be placed in the accumulator after memory is read to get the second number, and the ALU is actually instructed to perform the add operation. So the hardware signal for performing the memory reads and performing the addition will be sent to the ALU via the control bus. By the control bus. So what am I saying there? So first instruction involves moving data from memory into the accumulator. That's the first instruction. And there's a second instruction that actually fetches another number from memory, brings it back to the CPU on the data bus, and the ALU will be instructed by means of a hardware signal to do the operation. Right. So the question now arises, just to make things seem a little bit complicated. How do you fetch the first number from main memory? Well, from a logical point of view, to fetch anything from main memory, you need an address of a location in memory. You need to select a particular item in memory, and then cutting a bit of a short story shorter, you're going to read the memory. The memory is going to leave the number read from memory into a memory register, which needs to be transferred back to the CPU on the data bus. That's fine. Okay, that can be done by means of a controller issuing a sequence of correct control signals. I mean, it's like saying, okay, I want to move data which is in the memory register on the particular data bus, and I want to temporarily store it in the accumulator. It knows how to do that by means of issuing a sequence of hardware signals. So a clock pulse will trigger the operation to be performed. What do I mean by that? Well, I guess things all start to happen as a result of there being a clock present in the computer system. Every tick of the clock, something happens. The controller will issue a new hardware signal, and it takes so many clock pulses of data read from the main memory to get back to the ALU accumulator register. So everything's going to take place in synchrony with the clock pulse. Now, it doesn't matter too much. Our understanding of that at the moment doesn't mean too much to us at the moment. So the result of the operation is put into the accumulator by default, and just in case a further operation on the number that we've just obtained is required. And if you need to, the results that you've just achieved by telling the ALU to perform a particular operation can be saved safely into a specified memory location. I mean, supposing, I've just spent an hour getting a result that's been left in the accumulator, I can move the data in the accumulator to the safety of a main memory storage location. I just put it into main memory, in other words, so I don't lose it and I can get on with other things. So the ALU possibly looks like this. You've got a control bus coming from the controller into this. This typically signifies this shape. Typically signifies an ALU. What it means is that using the data bus, I can put enter data here, and that the first argument, the first piece of data will find its way into the accumulator, and then I can bring a second number and put it into the ALU, and then tell the ALU to take this number and the number that's just arrived and add them together by means of an addition control signal, and the result will automatically be left in the accumulator. And I'll ask the question, anything missing? Well, I've left out a bit of detail, and it doesn't really, it's inessential. It's just the idea of an ALU operates on two numbers. Both numbers have to arrive by being fetched from memory. Then, when that's happened, you can tell the ALU to actually perform the operation. Or it could be a minus operation, leave the result of subtracting one number from the other in the accumulator. Anything missing? I'm sure there's lots of things that I've forgotten about here, but anyway. So, how is the computer instructed to do all this? Well, the answer is by means of a very simple program using a language that it understands, such as the following. So the first instruction, along giving a sort of, instead of writing a string of ones and zeros, I'm giving you it in a sort of halfway house language between English and just binary bits. The instruction is load address 1. What does that mean? It means load the data, get the data to be found at address 1, put it into the accumulator. So load address 1. And the meaning of that is this. So this is a very short representation of the instruction. And the second instruction is simply, now add the data that you fetched from address 2 in main memory to the data that's already in the accumulator, and leave the result in the accumulator. Okay, so let's have a look at this. What's happened here? I've only got half my presentation here. So I've got a hunt. So I've got pages missing. How unfortunate. Never mind. To screen this. Right. Okay, so let's see. Right, okay. My screen froze at the moment, for a moment then. instruction. So where's this little program kept? I'm just giving you a 2-line program, a 2-instruction program. Well, it's going to be kept in memory, and each instruction will be stored in memory in the form of 1s and 0s. And maybe each instruction is going to be 16 bits long. The data used by the program will be stored here. So maybe I've got some location n and there's nothing there. Location n plus 1, this green area, I've got the first instruction. And at location n plus 2, I've got the second instruction that I've shown you above. Maybe location n plus 3, I've got a third instruction. Okay, so this is important. You store instructions and in memory. And you might say, well, okay, instructions involve memory locations, the specification of memory locations. So where is data stored in memory? Where's the data stored? Where is it? Where do you find it? Well, okay, that's not very helpful. The address of the first instruction is A, and then the next is A plus 1, then the next is A plus 2, and so on. The program counter will keep track of the location of the next instruction to be executed. So in other words, I'm operating with the idea that memory locations for a stored program have a first location, then a second, then a third, then a fourth, and then a fifth. And I can, if I know the address of the first instruction, I can store it in the program counter register. And after I've fetched the instruction, the first instruction, because I know where it is, it's kept in the program counter, all I have to do is to increment the address by 1 to know where the next instruction is, and I can go ahead and fetch that and so on. So the computer is hardwired to do the following things. First of all, fetch the instruction whose memory address is contained in the program counter, i.e. the PC register. It then increments the program counter by 1 so that it's ready to fetch the next instruction. And then the controller will decode and then execute the instruction. Okay, so what does that mean? It means that when the first instruction's been fetched from memory, controller is going to examine which instruction has been brought back. What does the instruction tell me to do? And then the controller will go ahead and do what the instruction is telling me to do. For example, add a number. In other words, what I have to do is to tell the ALU to add the number I just fetched from memory. Right, so little note here, refer to the blown up diagram of the controller added to this document. Decoding needs a bit more of a discussion here, but you can think of it this is the analogy. Supposing you receive an instruction and it's telling you to bake a loaf of bread, and the controller is prepared to do all that, but what it needs to know is what it must do in order to bring that about. What does it need to do to bring about baking of a cake? I mean, maybe maybe it has to heat up an oven. Maybe it has to mix ingredients. Maybe then, thirdly, it has to put the mixture, after it's been proven, into the oven for a fixed amount of time. So we're going to have to think a little bit about decoding a bit later on, but that can wait for the time being. So, instruction decoding. Okay, so it's a mean business here. So, instruction decoding is what's meant by decoding. It's done by the controller. The first few bits of the instruction is called the opcode, and the opcode abbreviates or represents an instruction to be performed. It's a short sequence of ones and zeros. So an example of an opcode is add, and maybe it's got a binary representation of 1, 0, 0. And what 1, 0, 0 means to the controller is that it's got to prepare for doing an addition operation. And as a result of decoding the instruction, one or more wires will be set to 1, control wires will be set to 1, in sequence possibly. For example, in an add instruction, the decoder will place 1s on the control bus to enable the memory to be read and to send its data to the ALU by means of control signals, coordinating that transportation of data from the memory via the data bus. And in addition, the add operation will select a control line on the control bus that results in the ALU being told to perform the add operation. In other words, to add the number that you just fetched from memory to the one contained in the accumulator, leaving the result in the accumulator. So the important thing is the controller, and this is very important, the controller is responsible for a sequence of actions itself to bring about any one of the instructions that it knows about. So, a small example I've been discussing will impress you on the need to cyclically fetch instructions from memory. And then for the controller in the CPU to decode them and perform the specified operation, which may involve reading data in the memory or writing data to memory. One possible operation is to place the results of an operation in memory at a particular location, say address. And this time the controller will actually put the address onto the address bus for it to be decoded by the memory decoder, and data will be written into the location specified. Okay, so that sounds, to me it sounds a bit complicated, but it's just a question of understanding some of the detail rather than horrendous complexity. So what I'm showing you here are 5 different opcodes, and I'm afraid I'm representing these in decimal. So in decimal 2, the meaning of that opcode, like abbreviation of an instruction, in other words, is store the contents of the accumulator in memory at a particular memory location as specified. So this in binary is obviously going to be 0, 1, 0. That's the binary equivalent to the store operation. 6 in binary, 1, 1, 1. Sorry, that's 1, 1, 0 it should be. 1, 1, 0. Simply add the data found at a particular memory location as specified into the accumulator. And 7, which is this is 111, 111. Subtract data from the number found in main memory from that's already in the accumulator. So because I've only got 1, 2, 3, 4, 5 codes, and it seems as though maybe I've got 8 different opcodes. I just need 3 bits to represent all possibly 8 codes. 3 bits. Okay, so hold on. I'll just spend a few more minutes looking at this quite important subtopic, and what I'd like you to do is to give lot of consideration to the following program. So here I've got 8 memory locations, and I'm addressing them by means of 0, 0, 0, all the way through to 0, 0, 7. So I mean I could translate those into 5-bit memory addresses in binary, but I'm not going to. So I'm just going to say first memory location, I've got this, contains this. Let's have a look at this. Look at this very, very carefully. I'll look at the first instruction. It's an instruction. How do I know? Well, 4 is actually the opcode that we looked at just a moment ago. What is 4? Let's just have a look at 4. It means load data into the accumulator. Load. Okay, so it says load data into the accumulator. So what is this? This is decimal 4. Well, really it should be 1, 0, 0 binary. And 0, 0, 5 is actually a memory location. It's this memory location. And let's have a look to see what this memory location contains. It contains the number 77. What does, let's have a look at the, let's supposing we've done that. We've actually put 77 into the accumulator. Let's look at the second instruction. That's a 7. I can't remember what 7 was. Well, let's go going the wrong way. 7 is subtract data from the accumulator. Let's have a look at that. So, okay, subtract, this is going to be, in binary it's going to be 1, 1, 1, 0, 0, 7. I haven't got rid of that. I should really make that binary as well. Contents is subtract the number found at this memory location, 0, 0, 7. Well, okay, let's have a look at 0, 0, 7. It contains the number 35. So, for the life of me, I can't remember. Okay, it was 77. Put that into the accumulator. Now we're being told to subtract 35 from the number found in the accumulator. Now, I reckon if my mental arithmetic is on this 42, leave that in the accumulator. Let's have a look at the third instruction. It says it's a 2006. Look at it. To store the contents of the accumulator in memory. So what we're doing here is to effectively save 42 that we've now got into the accumulator at main memory. Is it main memory 6? So main memory 6 already contains 42. I'm just going to store 42. I'm going to overwrite this 42 by 42. And then the fourth instruction is just 0, 0, 0, 0. And that means halt the computer. Just halt it. memory programmers because we can understand how memory contains a list of instructions, how we're addressing memory, we're addressing it in sequence. And at any particular time, the program counter contains the address of the next instruction to be executed. And we fetched the instruction at address 000. We found that it was a load instruction from location 05. That was the number 77. Leave it in the accumulator. And this instruction, this is the next instruction because we've added one to it. It says subtract the number found at location 007, which is 35, from the value in the accumulator, which was 77. That gives us 42. And the third instruction, that's PC plus 1, contents of the program counter plus 1, load the number into location 006. And okay, we've actually, seems as though we've already done that. We've got 42 in that location. This is the result of executing our very simple program. And so first and second instructions are giving you perhaps a clearer explanation than I've actually verbally expressed just now. So third instruction. So the third instruction is at 00T, so on. And fourth instruction, 003. Alright, okay, so the instructions at 0, memory location 003, sent to the memory. What comes back is 000, which is hold. So have a look at all that and really to come to. So here, okay. So here, originally, so what I've done is I should have given you. This is my starting table. One of the instructions I'm overwriting location 6 with 42, and I've got that here. The storage address 006 is overwritten. But I think that's clear enough. So this isn't obligatory, but it's we're just going back to what I've already spoken about, and it's just saying, well, okay, calculate what happens if 1 is put on input and on select and on read or write. So I've got a 1 here, that goes to 0. What happens? What's output? Just check that out. So these are just very simple logic gates. Not and this is what's called an RS flip-flop. Q contains its state, its value, for as long as you don't fiddle around with R or S. If you reset it, it changes to 0. If you set it, it returns to 1. So this is a fundamental memory cell. As a little exercise, so really, I mean, this isn't absolutely true. When I say calculate, we need to explore Boolean logic and truth tables. Well, I think I've explained those sufficiently at the moment. Okay, I think it's the end of this presentation. So, do you have any big questions on that, or is that, do you think with a bit of reading and a tiny bit of research you'll be able to understand all that? Because what I'm going to do now, if you haven't, Mohammed, I will continue by showing you what thank you, okay. say yes. You know. Okay, right. So go to that presentation. So just show you what I've given other students as their assess coursework. So, I mean, Michael hasn't told me whether or not he's expecting you to do this. I mean, the safest thing is, I suppose, if you were to do it, and I'll give you some extra time to do it, but we won't discuss this again. But what I will do is just to show you what I hopefully you can read that somehow. So we're going to have a look at cache memory next. Okay. And you would be able to do that if we just do a tiny bit more work on multiplication. So I'm asking you what's meant by the fetch, decode, execute cycle, describe the main hardware components. Well, we've done all that today, and I'll say a bit more about multiplication. And question C is easy. So I feel that what we're doing is probably like reason this scheduling is slightly trickier, and that's all contained in topic 1, and there's a video. So if you want to do that, this scheduling, not too bad. And I've got a particular question I'm asking here, and if you follow my notes, you shouldn't have any problems whatsoever in coming up with an answer to that. Okay, so we'll talk about these sort of practical issues a bit later on. So let me just go back to the first page. So as I said, I'm going to talk to you about cache today. And if we do a tiny bit more work on multiplication, you'd be able to do that question as well. It's pretty good going. Okay, that's easy, and the only thing that if needs be, I mean, we could have a second. Michael said I can have a second catch-up session with you. We could cover this as well. So it's entirely, what you want to do is entirely up to you. Okay, so do you need a break? Are you happy to continue? I'm going to have a drink of water. Yeah. Okay. Right. So let me load another presentation up. And what's this? Okay, so what we're going to talk about formally is this, but this is just guest terminology. And the thing I really want you to come to appreciate, to understand, and you might think it's actually trivial, very easy to understand, it's called the principle of locality, and it comes in two forms. Locality of reference is a fundamental principle of computing with lots of different applications, and I hope to be able to convince you of that by the end of this talk. So just consider the following situation: coronavirus distribution, how it spread. Today, one of the government advisors explained an alleged way in which the virus is transmitted. People that tend to visit hospitality sites like cafeterias, or in this country, public houses, or cafes, or whatever, tend to be social, and with a high probability will visit another hospitality centre within a short period of time, or a week. Hence, if one of those has the virus and visits such hospitality centre, because of closeness of contact and the nature of the closed air ventilation of the environment, there's a likelihood that as many as N people will be infected after a week, and so the virus is spread. So I'm relating locality, the principle of locality, to something quite humdrum, deadly serious, of course, but it's something that we probably wouldn't question. So we're going to start now. It's the virtual collapse of the classical memory hierarchy, part 1. So what is memory hierarchy? Well, let me explain it very simply. There are different sorts of memory in the world, and if you were to organise them, you could organise them into a pyramid, which shows you that at the top of the pyramid, memory is very expensive. At the bottom of the pyramid, memory is very inexpensive. And at the top of this pyramid, this memory hierarchy, memory has got very small capacity, and at the bottom of the memory hierarchy, or the pyramid, it's got very large capacity, like, multiple terabyte memories, and that's actually quite cheap to buy. And what else did I want to say? It's cheapness and the speed. Okay, and the other important factor is that as you go up the pyramid, the speed of operation of memory increases. So at the top of the pyramid, you have very, very fast memory. At the bottom of the pyramid, you have relatively very, very, very slow memory. So I'm going to use this session to introduce several important topics. We've just learned that computer systems on fetch, decode, execute cycles for computation to take place. In other words, the way in which a computer operates, it first of all fetches an instruction, brings it back to the ALU controller, decodes it, and then executes it. So in what follows, I'm not going to always explain the terms I'm using, but these at some point will be explained, and you will become comfortable with these ideas. So hopefully, no matter what your background is, that we have some idea that storage media varies enormously with respect to speed, cost, and storage capacity. Like I bought a very fast solid-state device, which is actually, it gives you much faster access to memory than classical hard disk technology. And the capacity was huge, in fact, but it was cheaper than hard disk. So there's this, there's this hierarchy. You can buy different sorts of memory, and they operate in different ways, and with respect to speed and cost and everything else. So there exists some very, very fast memories. I mean, probably they're so expensive that it's unlikely that you or I would actually buy them. Presumably if we had an application that required very fast memory access, we might invest a small fortune. In topic 1 we compared hard disk drive storage and compared it briefly with solid state disk storage, for example. But 80 years ago, or 90 years ago, I can't remember, prior to World War II, perforated paper tape was used. Well, it was just rolls of strips of paper on which many holes representing ones and zeros was used to input data or a program. Very, very slow to operate with. In principle, it's of unlimited capacity, but it is so slow, it's simply not used today. It's inefficient. Paper breaks, so you lose it. An old-fashioned computer could come to a grinding halt. But you might think of as an equivalent to cloud storage, which is incredibly slow at times. And I'm thinking about something like Asus Web Storage. So I don't know whether you have a terabyte of storage or you have a couple of terabytes of storage on your machine for next to no money at all. So it's a very large capacity distributed memory. I don't know whether it's based in Korea or one of the far eastern Asian countries. But it is very slow. It's very useful for storing a lot of material if you need to. But the question I'm asking is that, is there anything we can do by arranging things so that these differences in speed of all the different memories that you might want to use in a computer system, for example, access time ranging from seconds to nanoseconds, appear to disappear? In other words, you can get a system in which it seems that all the different memories that you're using in the system appear to operate at the same speed. Forget about the cost, because they're going to cost different prices, but the question is, can we arrange things so that these differences in speed appear to dissipate? Well, the answer is yes, if only on thinking about the problem for a second or two. And as the Germans would say, we can perform a Gedanken experiment, a thought experiment. And so, tell me what you think about this. Supposing I'm stuck with World War II paper tape, and supposing I want to use the data stored on paper tape on Monday, well, what I could do is to arrange for that data to be buffered. And what I mean by that is to be moved or stored onto a faster medium, maybe like a conventional hard disk drive, over the weekend, so that the data that I need to have available is immediately available and is accessible on demand on Monday. In other words, I'm going to spend the whole of the weekend reading data from paper tape and putting it somehow onto a hard disk drive. So I'm buffering it, I'm temporarily storing it onto a faster memory over the weekend, but it's going to take me the whole weekend to do that. But does the fact that you're having to spend a weekend really matter? You're not going to, on Monday, you won't notice the fact that all the data was originally stored on very slow storage. It wouldn't matter at all. Certain memories are so expensive, there simply isn't a market for it. Some of the fastest memory in existence is made from gallium arsenide. It's gallium arsenide devices that are made using this chemical, this element. And you might want to just quickly investigate the world's very fastest memory storage units. Certain memories are so expensive, but maybe you could, or you would be prepared to use a couple of registers for very special applications, because the time it takes to read and write data to a fast register is very, very, very fast indeed, and there may be some advantage in doing that. So the secret in providing a generally effective mechanism for collapsing the traditional hierarchy, and remember what that means. For traditional hierarchy, you're making it appear as though speed differences disappear. We have this idea of a hierarchy or a pyramid of memory types, and their speeds of each memory in that hierarchy is going to differ as you go down or as you go up the pyramid. The theory, the secret to do this is to exploit, to use what's called the theory of locality, of program reference and spatial reference. More specifically, a local application of that theory, which is called program locality. Well, the first thing I want to say in trying to explain all this is that locality, the principle of locality, is very, very, very general in its application, and it applies in every walk of life, every circumstance, almost every circumstance you can think about, and so on. So I don't know whether you've thought about it, but I'm going to ask you to think about the application of the theory of locality in a moment or two. So the technical phrase I just mentioned at the beginning of the section describes what we intend to do. We want to logically collapse classical memory with respect to memory storage as access time. I want to be able to treat any kind of memory as though it had the same relatively high access speed as the fastest memory in your system. So whilst our attention will be currently focused on memory within a PC or router, the general principles to more general systems such as internet service providers, wide area networks, PCs, or your very own laptop, and I don't know what I've got this virus super spreading to. Forget that, because I can't remember quite why I said that. I'm sure I had an interesting point to make that. So, okay, here we go. This is the serious bit. General principle of locality has two particular forms. First of all, it's spatial locality. It says something about space. And the second form is to do with time. It's the temporal form of locality. And both principles are typically couched in probabilistic terms and small periods of time. So let's just see if we can understand this and tell me what you think about the reasonableness of the two forms of the principle. So what I'm giving you here is a fairly formal statement, a rigorous and hopefully clear statement of locality here. So have a consideration of this. And I reckon this is spatial locality. Okay. If an event, no matter what the event is, if an event Z takes place in a particular location or locality or locale L, then there's a relatively high probability that the same event is also taking place in locality L1, where by hypothesis L1 is close to L, according to some metric. Well, the metric is to do with time, space, or some other metric. Okay, so let me give you a very concrete, non-computing illustration of what I mean. It's snowing in Bond Street, and therefore, according to the principle of locality in this form, there is a high probability that it is also snowing in St. Christopher's Place, which is just as the street off Bond Street, a couple of 100 metres away. Okay, so I mean that's a certain sort of plausibility. There's an event taking place, and in the very near future, the same event will be taking place in the nearby location. And I guess another illustration might be concerning an event such as your foot currently being in some position P, and there's a very high probability that in the next small interval of time, your foot will be in position P dash, where P dash is close to the location P, or another example, I don't know, I'm sure you don't wear spectacles, but if you're wearing spectacles at a particular time T, then there's a high probability that you'll be still wearing the spectacles at time T dash, where T dash is very close to T1. Or another version of that is that if you're wearing spectacles and you're in a sort of general physical location L, there's a high probability that you still will be wearing spectacles in the near future at location L dash, where L dash is close to L. Right? So I hope you think there's some plausibility and the truth of the two statements I've just read in connection with these ordinary everyday circumstances. So we're supposed to be relating this to programming or computing science, and I think I can make this understandable by talking about lists. And I'm going to call a list order maybe a shopping list. I mean, I'm coming back to something not computing, but the same holds in computing. You've got a list called myArray, and I can access each element of the list by writing an index number. Like an index number of 0 is in the 0th a position in the list, and my array 1 is in the second position in the list, and so on and so on and so on. Supposing I have a program that's currently accessing list items 34 to 87 in my list.
You are currently the only person in this conference.
Mohammed, have you gone? Mohammed? Are you still there? I'm sort of getting lots of yeses. Are you still here? Okay. The system just warned me that I was the only person in the meeting. So okay. Oh, that's great. Okay, so we'll carry on. I mean, we'll finish in about half an hour anyway. So supposing I've got a list and I'm actually maybe adding the costs of items on my shopping list, and currently adding the costs of items 34 to 87 up. In other words, I'm processing those elements on my shopping list. Then there's a very high probability that I will need to, or will want to, process items 87 to 88 in the near future. So here I've got an example of, from computing, like I'm processing a list, and what locality says is that I'm processing something in a particular region, then there's a very high probability that I will also want to process items in a nearby location. And in terms of the list, I've been processing items 34 to 87. There's a high probability that I will be processing 87 to 88 in the near future. And that seems to me to be a reasonable assumption to be made. So locality here is physical locality, in which the array is stored on some storage medium, like memory, main memory. And later on today, hopefully I've got time to do this, we'll look at some loops in programming languages. So I don't know whether you've ever thought about loops. You know what a while loop is? But in many programming languages, including Python and Java, you have program statements of the following form. While condition is true, process array with index I, and I is going to perhaps start with value 0 and go up to 1,000. So I'm going to process all elements of the list, all elements of the array. What I mean by processing, maybe just decrementing the value of the numbers stored in that list of numbers or something along those lines. So I think you'll see that the fact that most programming languages have statements like that vindicates the applicability of locality in terms of space. But the other principal sort of locality is called temporal locality, and the principle states the following. Well, this is another formal version of principle of locality. If an event takes place at time t1, there is a high probability that the same event will also take place at time t2, where t2 is close to t1. Okay, so let me ask you to think about your left foot and its physical position. Let me think in terms of 5 milliseconds time. There's a very high probability that your foot will still be in the same position. And I hope you agree with that. Right, let me give you another concrete example, not from computing. It's raining in Bond Street at 1 minute past 1 in the morning. Therefore, according to locality, there's a very high probability that it will still be raining there at the same spot at 5 minutes past. Well, that's plausible. Well, it's not absolutely guaranteed that it's going to still be raining, but there's a high likelihood of that. So, in the computer science context, what we find to be the analog to this Bond Street example, if a region of memory has just been accessed within a program, there's a high probability that it will also be accessed again in exactly the same location in memory, will be again accessed in the near future. And all I have to do, again, is to think about code loops or modules to understand temporal locality holds here. So here we've got it's a slightly different form of a while loop than I showed you a few minutes ago. It's while the variable c, while c has a value less than 200, repeatedly execute this block of instructions. I mean, maybe I've got 20 instructions there. And the idea is that maybe C starts with value 0, and every time I've executed the code block, I increment C by 1. So gradually, C will reach the point where it's 199. So I'm actually starting with C equals 0. I've executed the code block 200 times. Well, isn't this a very good example of there being a probability where, while loops are concerned, that you will repeatedly need to access in memory this block of instructions, and you'll need to access them again within a small period of time. So the point of my having shown you all this is that, so this sounds a bit technical, but it's not right. If we have two memories M1 and M2, and one's faster than the other, so I've got two memories M1 and M2, which differ in bandwidths. And what I mean by bandwidth is the speed of operations. Can't I choose a third memory called M, which has a bandwidth, i.e. operating speed, very close to that of memory M1, so that if I wanted to, I can arrange matters so that differences in bandwidth between M1 and M2 don't matter anymore, because when it comes to allowing access to what's in M2, when it comes to allowing access to what's in M2 to M1, I can simply put what I need from the slow memory M2 into the much faster memory M. M is close in speed to M1. And all I have to do is put what I need from slow memory M2 into the much faster memory M. So before I've got M1 here, M2 here, and M2 is slower than M1. What I can do is just periodically, get what I need from M2. Maybe the next instruction I need to execute in my program. But given the fact that locality is a very real principle, what I can actually do is fetch the thing I need from M2 and put it into fast memory M, so that I can give the item requested by M1 from M2 into, I can give it to M1, it needs that, and in the near future, so listen very carefully, so in the near future there's a high likelihood that M1 will need the thing it recently accessed from M2. This time it'll be here in very fast memory. So there'll be no delay. I mean, you can imagine that if M1 here needs to get data or the next instruction from M2, it's actually going to have to wait until M2, which is slow, delivers what it's got and it's transported to M1. Here, I'm getting something I need, M1 needs from M2. I'm making sure that it's put in, a copy of that is put into fast memory M, so that the next time M1 wants to access the same instruction, it'll be found in the fast main memory, and there will be a saving of time. And the time taken for instructions to be accessed from M2 might take 200 nanoseconds. But M1 has to wait, which is a complete waste of processor time, because in the space of 200 nanoseconds, I might have been capable of executing 1 million other instructions. That's a terrible waste of time. So you might think this is a bit of a joke, but it's not. If you find any of this troubling, think of the case that you wanted to read a book, perhaps to do some homework I set, and what you have to do, so forget it, you're not going to use the internet, you've got to go to a physical library, and you do some work and you return home. And a bit later on you decide you want to do a bit more work and you need to refer to the same book perhaps because something you need to check out, so you have to go back to the library. And all this takes time, and at the point where you need the book, you'll have to spend time travelling to the library. A whole hour on London's Underground. What a waste of time. You could have been working on your homework. So the solution is that you take the book home so that you can access it immediately. This is like caching the work that you need to refer to. There's a high probability you've got the book. There's a high probability in the future you will need to access the book again. So take it home. Make use of the fact, exploit locality. You're taking the book home, or you're buying the book, so that you won't have to spend hours travelling to and from the library. An even simpler example of all this is when you sit down to work on your homework, you collect all the things you need by your side. You've got your laptop, you've got the Wi-Fi connection, you've got your microphone, you've got a textbook, you've got all your notes, you've got access to Pharos and so on. So just say a little bit more about this. Right, so part 2. anticipation of what's needed ahead of the point of need. If you can anticipate the next block of instructions that you're going to need and load them into memory M, then when M1 needs more data, needs more instructions, these can quickly be loaded into M1 from M. Well, one way of anticipating or predicting instructions or data is given by locality. It says if you access a block of code in slow main memory, there's a probability that you'll need to access that same block of code again. So the answer is if you anticipate using data or instructions from slow main memory, you put them into fast local memory. And so this is probably a little bit much to take in at the moment. But what we spent doing at the first part of today's session is that we looked at the CPU, we looked at the very simple computer architecture. But here's the CPU, and we know that the CPU splits up into controller and an ALU and two registers and so on and so on. And what I'm showing you here is a data bus connecting the CPU with I call it a register, which is associated with memory. And it's not a terribly good diagram. What this thinner black line represents is an address bus. This connects to another register which can hold a memory address. And what I think I've made reasonably clear this morning is that the CPU can fetch data or the next instruction by putting an address, giving the address to main memory, and then the CPU telling the main memory to do a read. So the data comes out and is put into this register. Then the controller can actually make sure that the data that's just been read from memory is transferred all the way back to the CPU. Or another possibility is that the CPU wants to write some data to main memory. It's like store, our store instruction. Wants to store data. What it needs is an address in memory in which to store. And it puts the data to be stored at this location in memory into this register. Then the CPU's controller will say, okay, memory, do a write from this address using this data. This data will be transferred and stored in main memory. But what we're looking at now is the presence of fast memory. It's called cache memory. And to help integrate, to make the whole... So anyway, everything above this curly red line is what we've looked at already, and we've looked at today. There's a slightly different format, but what we're looking at now is the addition to some fast memory called cache. It's expensive, it doesn't have enormous capacity, and to help us integrate cache into the system, we've got something called a CIC, a cache interface controller. And I'm just going to just looking at the time at the moment. I'm just going to explain what happens to the system when whenever the CPU wants to fetch data or an instruction. Let me tell you, it's going to attempt to read data from this address, but it's going to make sure the address main memory is put into this address register. And then the CPU says, look, I want to do a read from main memory at that address. So what happens in parallel is that the kick tells main memory to do the read. To do the read. So it's going to wait something like 500 nanoseconds data to appear in this register. But at the same time that the kick sent main memory that instruction, hardware signal, to do a read, kick is actually telling cache to tell it whether or not cache contains a copy of the contents of this main memory address. And within a split second, faster than you can blink your eyes, the cache will return what's called a hit or a miss signal. Hit if it knows about what's being requested, a miss if it doesn't know what's being requested. Let's, for the sake of argument, assume that cache doesn't know anything about this address that's being read from them. In other words, it hasn't got a copy of the contents of that address inside. What will happen is that main memory is allowed to complete its read operation, and the cache interface controller will tell the CPU that you can get the data that you've asked for, it's ready, and I'll put it on the data bus, you can get it. But what also happens at the same time that's being done is that a copy of this data will be put into cache. The copy of the address will be put into cache. So it's as though cache contains, first of all, an address followed by data. And that's all put into cache. But let's think, just for a second, one further possibility. So a little bit of time elapses. The CPU again wants to read the same memory location. It puts an address into the address register, and the cache interface controller is going to say, okay, memory, do a read. But then, as before, kick checks cache to see whether it knows anything about this address, and instantly, almost instantly, cache will, something like 50 nanoseconds rather than 200 nanoseconds later, cache will actually tell the kick that it's got a hit. In other words, what happens very, very quickly is the kick will actually put the data it's got into this memory register. The read command will be aborted to main memory, and the CPU finally says, okay, one of these lines is going to say, CPU, yep, all set up. You can go ahead and pick the data that you wanted in this register. And what if happened, and this is all because of locality, the fact is that there's a high probability that if you access memory once, there's a high probability that you're going to access it a second time in the near future. And what we did was to make sure that the bit of memory that was accessed is copied into cache, where we know that there is a high probability that the CPU will want to access that location. This time it's in cache, and we can save 150 nanoseconds by putting it into cache. Anyway, I've given you lots of notes, but you don't have to look at all that. It's just I want you to understand locality, and I mean there's tons of, there's more than you actually need for this course here. And don't, whatever you do, dare look at page 17, 18, 19. Okay, so just going back to my screen. Oh goodness, we've got 10 minutes left. That means I can actually finish what I wanted to finish. Okay, and that's let me show you this. And I mean, you can, if you want, if you're really fed up, you can go if you want. Yeah, just go. All right. I'm going to upload a second presentation, so I'm going to find it. It's uploading. So I just want to, I mean, this is quite an intense session we're having here, but what I'd like to do is just to sort of bring to closure some of the work that we've been doing on assembly, on the assembly. And what I want you to do is to show how, using assembly, our opcodes in other words, we can write a program that computes m multiplied by n for any number m, any number n. Program can actually work out what m times n is. What we've looked at so far is store, add, sub, the whole, some of the instructions that we've looked at today. And well, I'm going to show you this, and you can spend time looking at this in the future. This program is capable of computing m multiplied by n. And I want you to think about multiplication, and you can define what it is to multiply two numbers m by n simply as the following statement. You repeatedly add m to itself n times. So m times n is simply equivalent to m plus m plus n plus n plus n times. So hopefully you agree with that. I really wanted to first of all talk about while loops, so if we have another opportunity, I can just say a little bit more to finish everything, some sort of conclusion. But can I show you what I'm doing here? I'm adding, let me just go back up. So I'm adding two things. I'm adding an operation, an opcode called jump not zero, and I'm adding something called a label. Here I'm labeling a memory location or a particular instruction, and 9 0 1. Just going through this. Okay, I think, to be honest, I'm not actually giving you the precise location. So Mohammed Can I just ask a question? Would you, so that we can finish this first backup session to completion, would you prepare to do another another session on Pharos on Monday night for an hour, just 1 hour? Would you be able to do that? I'm not quite sure. I mean, it doesn't have to be Monday. It could be Tuesday, or it could be earlier, and we need to decide on a time. Or in fact, okay, yeah, wait a minute, let me list it first. Thursday, if it's okay. Thursday's actually probably a bad time. I mean, can we just spend about 10 minutes? Can you spend an extra 10 minutes now? And then we'll talk about meeting again for, I mean, maybe next weekend or something like that. Would 10 minutes be okay? I'm still recording all this. So, can we just spend about 10 minutes now? And what I want to do is just to look at this. Right? So, so what I've got here are abbreviations for memory locations. So, for example, A2, I'm using A2 to represent this memory address 0010. And in this memory address, I've actually got, I've made a correction here, I'm sorry about it. It's store in A9. Okay, store, not A8, store the number in the accumulator that's, and put it into memory location A9. So A9 is this location here. At the moment it contains just a number M. So have a look at this. L1 is a labeled it's called a labeled statement. And the one opcode that I'm introducing is jump not zero. And I'll explain that very briefly. A jump not zero opcode means, jump not zero instruction means, look at the value of the accumulator. If it's not zero, then jump to the instruction that has label L1. Jump not not 0. Look at the accumulator. If the accumulator's value is not 0, then literally jump to this instruction here and start executing again. So can I take you just through this short program, which I'll try and give you a better copy of this because I've made 2 corrections here. First instruction is load the number found in location A8. Okay, here's A8. What's in A8? The number M. Put that into the accumulator. So the accumulator contains number M. Second instruction says add the number found at location A9. What's in location A9? It's M. So I'm going to add M to the value of what's in the accumulator. Let me ask you, what is in the accumulator? It's the number M. So I'm adding M to M and put the result into the accumulator. That's what add A9 means. So what happens is that twice M is going to be put into the accumulator. And what I'm going to do is to store what's in the accumulator at location A8. So what's in A8? Well, at the moment it's M. So I'm going to replace that by 2 M's, twice M, 2M, because I've added M to M, got 2M. So you're going to have to remember that in A8 I've got 2M. So what do I do here? This is the 4th instruction. It says load into the accumulator the number held in location A11. Well, what have I got in A11? It's the number N. And the next instruction is DEC, which just means take away 1. DEC means subtract 1. So I've now got N in the accumulator. I subtract 1 and I'm left with N minus 1. And then I store what I've got in the accumulator back into A11. Here's A11. Did have the number N. I'm going to replace that with the number N minus 1. And then critically, what I'm going to do is to look at the value in the accumulator, which is N minus 1. And I'm assuming that N is a number like 10. So the value in the accumulator is certainly not 0. So what I'm going to do is to jump to L1 again. So we're going to start all over. And that means add the value in A8. Well, what have I got here? If you remember, I've got twice M. Put that into the accumulator. Add the number in A9, which is M.
You are currently the only person in this conference.
No, Mohammed, don't go. Where are you? Oh, you've got headphones now, have you? Alright. So, what I've got now in the accumulator is 3M, because I've just added M to 2M. Store the result in A8. So I'm getting rid of it. It was 2M. I'm now replacing this M by 3M. And then I'm loading the value of A11, which is now, if you remember, it's N minus 1, into the accumulator. I'm decrementing the value of the accumulator by 1. I've got N minus 2. Then the next instruction says, okay, so store the value N minus 2 in A11. So I've done that. Still got, I think it's M, I'm losing myself a little bit, N minus 2 in the accumulator. Jump if the value of the accumulator is 0. It's not 0. Take A out. Well, it's not N minus 2. It's not 0. So I'm going to repeat all those instructions again. And hopefully you can see that by going through all these instructions, I'm going to decrement N repeatedly by 1 time I'm adding m to m. So I'm going to add m to itself n times. And finally, I'm going to, this location A8 will contain the result of multiplying m by n. And eventually, what's put in the accumulator is 0, because, maybe I start off with n equals 10. I'm going to decrement it by 1 repeatedly until it becomes 0. And jump, not 0, well, this time I skip. I don't loop back to L1. I just hold the computer. And what I'd like you to do is just try and just think a little bit about this program. The reason I'm asking you to think about this, and we can talk about this program again if you want me to, is that it does appear on the assessed coursework. Right? I'm being very helpful here. Right? So have a look at this. It's all based on everything we've done today. We've looked at opcodes, and here I've got load A8. If you remember, the opcode for load is decimal 4. A8 is an address at 1001. 1001, that's A8. Everything ties together. Load A8. That's the address A8. It's the opcode for load. The reason I'm asking you to understand this little program is that, well, actually, we never ever had an opcode for multiply. We had addition, and as long as we know how to define multiplication in terms of repeated addition, then we can write a very short program to do multiplication. And I reckon that to have this as an outcome at the end of the first topic that we've studied, computer architecture, together, it's quite an achievement. Okay, so I don't know whether you agree. So Mohammed, can I ask you what the future is going to be? Michael said I could have another session this weekend with you, but maybe, if you are going to do the coursework, have another week and we can discuss another 2 areas next weekend. We could do that next weekend. Entirely up to you. So just let me know. Yeah? What do you think? So I could have an hour on Monday. I could have a 2.5 hour session on Saturday next week, or 2.5, and a 2.5 hour session on Sunday next week. Absolutely up to you. Whatever's best for you. Well, how about an hour on Monday? It could be Monday afternoon. Could be Monday at 4 p.m. London time. Just write that. That's one possibility.
Oh, I think it might be here. Hi. I think the shopping's here, Karen. Hi. Thanks a lot.
Oh, there's a few things that I think the substituted that I don't want. Yeah, there's a couple of things. Yeah, I think I've got an email to say I can't substitute.
Can you go through this?
Yeah, I'll go through them. Thank you.
Do you want us to take it into the kitchen?
I'm not actually. I've got that on. If you just drop it there, I'll come and pick it up.
good up. So.
No, it won't.